Welcome to STEM Professionals. In this video, we will discuss the problems and conceptual exercises of Chapter 2 from the book James S. Walker. So let's start with the video. So here in this question, we are given that when a chameleon captures an insect, its tongue can extend 16 centimeter in just 0.10 seconds. Now there are three parts in this question that we need to solve. In the A part, we have to find the magnitude of tongue's acceleration. And we can assume that the acceleration remains constant throughout the motion. Now let me first show the coordinate system. So this is our positive x direction. And here this is x0, which is equals to 0, and here it is x, where this value is 16 centimeter, or we can write 0.16 meter, and time to reach this much of distance is given to be 0.10 seconds. Now to find the acceleration, we can use this equation which we derived earlier. X is equals to x0 plus v0 t plus half a t square. Now x0 we have 0, so this term would be 0. Now initial velocity, here this v0 is also 0 at the initial position, so this term would also be 0. So we are left with x is equals to 1 over 2 a t square, and from here, rearranging the terms, we can write that acceleration is equals to 2x divided by t square. Now we can put the values. So 2x we have 0.16 meter divided by t square. So t we have 0.10 second and its whole square. Now we can solve this by using our calculator, and we'll get the acceleration to be 32 meter per second square, which is very high. So this is the answer for the A part. Now next, in the B part, we have to tell that in the first 0.050 seconds, does the tongue extends 8 centimeter, or it is equals to 8 centimeter or less than 8 centimeter. So what the question is asking, that at half of the time, like at time t equals to 0.05 seconds, what would be the position of the tongue? This position, would it be greater than 8 centimeter, would it be less than 8 centimeter, or equal to 8 centimeter? This is what the question is asking. So now here we see that the position varies with the square of time, because acceleration is constant, so x is proportional to t square. This thing we can write. So displacement will be less than half of its final value when half the time has elapsed. So the correct answer would be that the position would be less than 8 centimeter because of this relation, x is proportional to t square. Now next, in the C part, we have to find the extension of the tongue in the first 0.050 seconds. Tell the exact value, what would be the position when the time is 0.050 seconds. Simply we can put the values here. So x is equals to 1 over 2. Acceleration we have already calculated. This is 32 meter per second squared times t square. Now t we have to take to be 0.05. So 0.05 and it's squared. Now we can solve this by using our calculator, and we'll get the answer to be 4 centimeter. Therefore the position at this time 0.05 is less than 8, which is equals to 4 centimeter. So this is the answer for the C part. So here we are given that this boat is cruising in a straight line at a constant speed of 2.6 meter per second. So initial speed we have 2.6 meter per second. Now then it shifted to neutral and it start coasting for 12 meter. So this distance we have, let me show it on the figure. So this distance we have 12 meter. So after costing for 12 meter, the engine is engaged again and the boat resume cruising at the reduced speed of 1.6 meter per second. So here the velocity becomes 1.6 meter per second. Let me first describe the coordinate system also. This direction we have taken to be positive, so this is positive x direction. Now there are three parts in this question that we need to solve. In the A part, we have to find how much time did it take for the boat to coast 12 meter. So how much time does the boat takes to reach from this position to this position? So let this be x naught. This is equals to 0, and here the final position becomes 12 meter. Now let us find the average velocity from this position to this position. So average velocity will be equals to 1 over v naught plus v. So that would be equals to 1 over 2. V naught we have a 2.6 and v we have a 1.6. So that would be equals to 2.1 meter per second. Now we can easily calculate how much time did it take to reach from this position to this position. So time t would be equals to delta x over the average velocity. So delta x we have a 12 minus 0, which is 12 meter. Average velocity we have 2.1 meter per second. So this would be equals to 5.7 seconds. So the boat takes 5.7 seconds to reach from this position to this position. Now next in the B part, we have to find the boat's acceleration while it was coasting. So during this time interval, we have to find the boat's acceleration. Now for that, we can use this equation. V is equals to v naught plus at, and from here we can write that a would be equals to v minus v naught divided by t. Now we can put the values. So a is equals to, now we are given with the 1.6, so 1.6 meter per second, minus v naught we have 2.6, so 2.6 meter per second, divided by the time it took is 5.7 seconds. So this would be equals to 5.7 seconds. So from here we'll get the answer in negative 0.175 meter per second squared. Now where this negative sign, what does it denotes? It denotes that the direction of acceleration is opposite to the direction of motion. Like if I show in the figure, the velocity of the boat is in this direction, but the acceleration would be in the opposite direction, like this. So this is the answer for the B part. Now next in the C part, we have to find what was the speed of the boat when it had coasted for 6 meter. Now when the boat reaches here at half the position, this is x equals to 6 meter, then what would be the speed of the boat? This is what we have to calculate. Now for that, we can use this equation. V square is equals to v naught square plus 2a delta x. V naught square, so v naught we have 2.6, so this would be 2.6 and it's squared, plus 2 times, now acceleration we have calculated to be negative 0.175 meter per second squared. Now delta x what is delta x? This is xf minus xi. In this case, C part, this would be the xf. So 6 minus 0, that is 6. So 6 meter. This is equals to v square. Now v would be equals to under root of this value. Now we can use a calculator to solve this, and we'll get the value of v to be nearly 2.2 meter per second. So this would be the speed of the boat when it had coasted for 6 meter. So the infamous chicken is dashing towards the home plate with a speed 5.7 meter per second. So here the speed we have v naught is equals to 5.7 meter per second. Now then the chicken slides for 1.2 seconds, just reaching the plate as he stops. So here the velocity becomes 0 and the time interval, this is t equals to 0, and here this time t equals to 1.2 seconds. Now there are two parts in this question that we need to solve. In the A part, we have to find the magnitude and the direction of the chicken's acceleration. So before proceeding with the A part, let me first define the coordinate system. This is our positive x direction, and here the x0 is 0, initial position, and here the final position x. Now the acceleration. So for that we can use this equation, v is equals to v0 plus at, since we know the final velocity and the initial velocity and the time also. So from here acceleration would be equals to v minus v0 divided by t. Now we can put the values. So final velocity we have 0, initial velocity we have 5.7 meter per second, divide by time is 1.2 seconds. So from here we'll get the acceleration to be equals to minus 4.8 meter per second squared. So what would be the magnitude of acceleration? So magnitude would be 4.8 meter per second squared. Now next, the direction. So this negative sign shows that the direction of the acceleration is just opposite to the direction of motion. Let me show it on the figure. So this is the direction for velocity. So the direction of acceleration would be like that. This would be the direction. Now next, in the B part, we have to find how far did the chicken slide. So this distance we have to calculate. How far it slide? This distance. Let it be delta x. So for that we can use this equation. Average velocity multiplied with time, this would be equals to delta x. But we don't know the average velocity. Average velocity we have 1 over 2 v plus v0. This is the definition for average velocity for constant acceleration, multiplied with time. Now we have all the values, we can plug it here to find delta x. So this would be equals to 1 over 2. Final velocity becomes 0. Initial velocity we have 5.7. So 5.7 meter per second, multiplied with the time is 1.2 seconds. So from here the value of delta x comes out to be as 3.4 meter. So this is the distance traveled by chicken before coming to rest.